called tray spacing. Distance between the two trays, this is one tray, this is another tray. This distance is called tray spacing. Since the liquid is coming in this way, so this weir is called inlet weir, W-E-I-R, inlet weir, and this is outlet weir. This is outlet weir. This is inlet weir. Fine. You are understanding that based on this outlet weir, the liquid height basically depends on this height, outlet weir height. Liquid height over a tray depends on the height of this portion. Fine. So by this way the separation occurs. As I told in the last class, here the more volatile component has the tendency to leave the liquid phase to vapor phase, and least volatile component has the tendency to leave the vapor phase and come to the liquid phase. By this way mass transfer occurs.
Sir, I have a question.
Tell.
Sir, why doesn't the liquid fall through those holes in the sieves?
Yeah. Anyone can give the answer? Let me again show that.
Sir, can it be any membrane kind of thing?
Yes.
Sir, can it be any membrane kind of thing which allows only vapor to pass and not the liquid?
No, how membrane can retain the liquid? I mean, obstruct the liquid.
By selective lipid removal.
His question is only vapor is moving up, liquid is not moving down through these holes. Anyone can give the answer?
Sir, vapor pressure restricting water molecules to come down.
Yes, this is the correct answer. The pressure is maintained such a way that the liquid cannot fall down, but vapor can move up. So which portion of the distillation column has the highest pressure? Top or bottom? Which portion of the distillation column has the highest pressure? Top section or bottom section? Anyone?
Section.
Top section.
It's wrong answer.
Say bottom section.
The
Yes.
bottom section.
If it is top section, how it is moving up then? The vapor? Bottom section has the highest pressure, and top section, especially the pressure of the condenser is the lowest. The pressure in the reboiler is the highest. Okay. But remember, here if vapor, the pressure at which the vapor is moving off, if that is very high, the liquid may come out and it may be entrained. So that is called flooding. The pressure of this vapor stream has to be maintained properly. If the pressure is reasonably high, this vapor will push the liquid off and it leads to flooding over this tray. So this flooding also will be discussed, I hope, in your mass transfer. If flooding occurs, naturally the separation efficiency is degraded. Okay, let us come to our original part. Basically, we are doing degrees of freedom analysis for distillation column. Come back to that distillation column. This is a distillation tower. Fine. We have discussed this in the last class. So you see this feed is basically enters on a tray. So this is basically the feed plate. And this feed plate is basically here we have considered 10th plate. Okay. So bottommost tray is first tray, second tray, feed plate or feed tray is the 10th tray, and topmost tray is the 20th tray. So this tower includes 20 trays, one reflux drum and one reboiler. Sometimes it is considered 22 trays. Okay, so in the tower there are 20 trays total, and we have one condenser reflux drum system. This is also considered as a tray, and reboiler column base. This is also considered as a tray sometimes. Sometimes I am telling. Okay. Yeah. Now you try to understand these assumptions. So before developing the model of any process, we need to adopt or consider a couple of assumptions. So for this example, distillation column, we are adopting these assumptions. Our first assumption is feed is a saturated liquid. Feed is a saturated liquid. I mentioned yesterday there are 5 types of feeds. So here we are considering it is as a saturated liquid. Second one is quite common assumption for most of the processes, that is no heat loss. It means the column is perfectly insulated. There is no heat loss from the column to the surroundings. It is only possible if the column is perfectly insulated. Third assumption. All the trays are 100% efficient. It means tray efficiency is 100%. Tray efficiency is 100%. Accordingly, we can tell that the trays are ideal trays. The distillation plates are ideal plates. Fourth assumption. Negligible vapor holdup on each tray. See, this holdup we are representing by the unit mole. Holdup has the unit mole. So naturally, this is a reasonable assumption. We can neglect the vapor holdup. The reason is written here within the bracket, you see. The density of liquid is much higher than the density of vapor. Liquid density is much higher than the vapor density. That's why it is reasonable to assume. Fifth assumption. You note down this fifth assumption and let me know what is the meaning of this. Roll number 10030, Pooja Sharma. 10030, Pooja Sharma. Can you hear me? 10029, Praneeth. 10029, Praneeth. 10035, RJ Reddy. 10035. 10037, Rohit.
Yes, sir.
What you understood from this point?
So when the vapor and the liquid containing both A and B are mixing on the trace, this point means that if like 1 mole of A from the vapor goes to liquid, then the energy released is enough to vaporize the liquid, vaporize A from the liquid to vapor, like equal amount of A from liquid to vapor and vapor to liquid.
Okay. So can I tell like this way? If 1 mole of a component condenses from vapor to liquid, exactly same mole of component transfers from liquid to vapor. Can I say like this?
Yes, sir, yes, that is what I was trying to say.
Yeah, basically if there is 1 mole of vapor condenses at the same time, exactly same mole of liquid gets vaporized. Okay, so that means there is no accumulation kind of thing. So this is the molar heats of vaporization. I mean, yeah, it's sometimes called as equimolar overflow. In mass transfer, it is popularly expressed through this term, equimolar vaporization. So I think you understood. If 1 mole of vapor condenses, exactly same mole of liquid vaporizes. This is the assumption. Okay. Now our sixth assumption is perfect mixing on each stage, which is quite common for most of the chemical processes. In fact, I mentioned few assumptions are very common. Perfect mixing on each stage. What is the meaning of this? Roll number 10024, Muskan Jain. Can you hear me, Muskan? 10001, Abbas Sarkar.
Yes, sir.
Yeah. What is the meaning of this? Perfect mixing on each stage. What do you understand by this?
Sir. Means equal number.
Okay, 18 CH 30016. 18 CH 30016. Ravi Kiran,
Yes, sir.
tell what do you understand by this sixth assumption?
Uh, I guess mass transfer between liquid, I mean, in each stage takes takes place if liquid and vapor.
Roll number 19 CH 10001. Avilas Sinha. 10001 Avilas Sinha. 10003 Adarsh Kumar. 10003 Adarsh Kumar. 10010 Ankit Bharma. Ankit, are you there? Mainak Paswan 10022. Mainak Paswan 10022. 10031 Rahul Golar. Rahul, are you there? 10032 Rahul Kunawat. 10032 Rahul Kumawat. Anyone can give the answer? What is the meaning of this?
Sir, does it mean that through the mixture there's no variation in properties like temperature or
Yeah, what's your roll number?
concentration? So 19 CH 30036.
Correct. It means the composition everywhere on the tray is same. Temperature everywhere on the tray is same. There is no basically spatial deviation. There is no deviation of temperature with reference to space. This is the meaning. Yeah. Next, come to this point. Relative volatility of two components remains constant throughout the column. Relative volatility, which is denoted by alpha. Relative volatility, which is denoted by alpha. It remains constant from top to bottom or bottom to top. We'll discuss later what is this relative volatility. Fine. We'll discuss this relative volatility term. What is this? Eighth assumption, liquid holdup varies from tray to tray. Liquid holdup varies from tray to tray. So this we will observe through our modeling equation. Like we have considered in fourth assumption, no vapor holdup is negligible. But here we are considering liquid holdup is a variable. And it will have a differential term. We will see this liquid holdup variation when we will model the distillation column. Ninth assumption, you see, condenser and reboiler dynamics is neglected, particularly thermal dynamics. That means we are not going to do any energy balance equation for condenser and reboiler. We are not going to do any energy balance equation for condenser and reboiler. The thermodynamics is neglected. Yeah, I think these are the assumptions. Based on these assumptions, let us develop the model for the distillation column. You see what I have written at the top. Based on assumptions 2, 4 and 5, we can write all vapor flow rates are identical. Think deeply. Can we write this or not?
So there may be slight difference because like the reason is like from getting bottom to top, some vapor molecules may be condensed.
Yeah, that is assumption 5. If there is any condensation, equal amount of vaporization occurs. See, what you are saying, it is against this assumption. If there is any condensation, equal mole gets vaporized. That means there is no change in terms of moles. See, these are the molar flow rate, moles per unit time, like mole per minute, something like that, or kilomole per hour. So according to fifth assumption, no. What vapor is going in, equal amount of vapor is coming out.
So in practice, wouldn't assumption 5 be wrong most of the times because it is very difficult to find two components of such exact properties, right?
It is very true. It is very true. It's a bad assumption. In fact, when we go for rigorous modeling, we do not consider this. It's really a bad assumption. But at this preliminary stage, let us go with this. Okay. But you are very correct. This assumption is not realistic at all. But at this preliminary stage, let us go ahead with this. Yeah, so can we write this? You all agree or anyone disagrees? See, you just think like this way. Suppose assumption 2, what is that? No heat loss. No heat loss means there is no effect on this tray temperature. Okay. Now, what is fourth assumption? Negligible vapor hold up. So what vapor is entering, that is going out. There is no hold up. There is no accumulation of vapor here. What is going into a tray, exactly same amount is going out. There is no vapor hold up. It means exactly same amount is going out as it is going in. And fifth assumption, if there is any phase change from vapor to liquid, exactly same number of moles participates in phase change from liquid to vapor. Okay. So because of these reasons, or based on these three assumptions, we can write this. Vb equal to, all these vapor flow rates are identical. Fine. So basically, we have another course like process modeling and simulation, your elective course. You have one elective computer methods in chemical engineering. So there the rigorous model of the distillation column is discussed. And during that time, you will see that most of these simplified assumptions are relaxed. Okay, but at this beginning stage, let us go ahead with this as I told. So I hope this is clear to everyone. All the vapor flow rates are identical and that is equal to V. I mean, we are denoting by simply V. But remember what is written in this bracket. They are identical, but they are not constant. That means if there is any variation with time in VB, all the vapor flow rates will change. Because you know, the change is starting from this bottom only, VB. If there is any change in VB, all the vapor flow rates will change. So usually the change in vapor flow rate occurs from this bottom section. Fine. Now you note down the notations, although you know all this. In fact, I have mentioned, but still. You note down all these notations. Since we are going to compute all these variables, we have to know the units of all these mathematical terms, all these notations. Okay, so let us come to the model. So we'll go to model, you know, by making envelope. So this is our topmost envelope. This is the topmost section of the column. You just see what I have drawn in the right hand side. It is condenser reflux drum system. Condenser reflux drum system. As I mentioned before, the composition of liquid in this reflux drum is same with the composition of reflux and distillate. The composition of the liquid in this reflux drum XD is same with the composition of reflux and distillate product, because the same liquid we are recycling to the column and we are withdrawing as the top product. So I think it is very straightforward to develop the total mole balance equation, which is written in the left hand side. You see, this is the total mole balance equation. I have shown that this MD has a unit of mole. V20 is the input, R and D, they are two outputs. So accordingly, we can write this total mole balance equation. Fine. Now come to the component mole balance equation. You see, in the component mole balance equation, I have just multiplied all the terms with their corresponding or respective composition. In the component mole balance equation, all the terms present in total mass balance are multiplied with their respective compositions. So can you simplify this component mole balance equation and write in the form of dx dt equal to what? I repeat, you just simplify the component mole balance equation and let me know in the terms of dx dt equal to what? Keep dx dt in the left hand side and let me know the right hand side terms. Let me know dx dt equal to what?
Sir, is it V20 into Y20 minus XD divided by MD?
Yeah. What's your roll number?
19CH10002.
Correct. Abhishek.
Yes, sir.
All of you got this equation, final equation, dx dt. See, I have just substituted, I mean, you need to substitute this total mole balance equation here. Then you will get this dx dt. Room number 10038. Tanay Gaurav. 10038. Tanay Gaurav. 10045. Sankalp Bose. 10045. Sankalp Bose. Okay, fine. All of you got this equation? Students?
Yes, sir.
Okay. So this is the condenser reflux drum system. Okay. The next section or envelope is the topmost tray. See, we are coming from the top onward, top downward. Okay. So this is the top section of the column. Next section is the top tray. That is 20th tray. Okay. You see the schematic. This is the schematic for the top tray, which is 20th tray. And you see here the nomenclature. The stream, the suffix indicates the tray the stream left. Like this one L20, that means liquid stream leaving 23. Okay, B20 means this vapor stream leaving 23. Here B19, that means vapor stream leaving 19th tray. It is coming from 19th tray, okay? So nomenclature is given accordingly. And RXD, they are different because, that is reflux rate, and XD, it's corresponding composition in mole fraction. In this process control course, we are basically developing the dynamic model of the distillation column. But in your mass transfer course, static model is considered. Okay. I repeat, in this instrumentation and process control course, we are developing the dynamic model, because you see this term is there, DMDT. So it is the dynamic model. But in mass transfer course, this will be considered as 0. Left hand side is 0. Now, reason I told that if the process operates all the times at steady state, there is no need of any controller. If the process operates at steady state, there is no need of any controller. So because of the some disturbance effects, or to reduce the effect of the disturbance, we are going to design the controller. The process is almost always or frequently disturbed by the load variable or disturbance variable. That means the process has the intention to deviate from the steady state. Therefore, we are doing dynamic model, and therefore we need controller. Yeah. Similarly, can you write this component balance equation in dx20 by dt and tell me the right hand terms? You simplify this component mole balance equation, keeping dx20 dt in the left hand side. Let me know the right hand side terms. In the similar fashion, you write the component mole balance equation, keeping dx20 dt in the left hand side. What are the right hand side terms? Let me know. Anyone?
Sir, is it 1 by M20 into V20 into Y19 minus Y20 plus R into XD minus X20?
V20 you got.
Okay, so V20 equals VB. I made V19 equals V20.
Okay. Yeah, they are identical. Yeah, correct. Yeah. What's your roll number?
19CH30036.
Yes. Everyone got this?
Yes, sir.
Good. Yeah. So what is the next section? See, as I told, we are moving from top downward. Okay. First, we have considered condenser cum reflux drum. Next, top tray. Next, we can consider 19 to 11th tray or 11 to 19 tray because there is no change of notation. Fine. That's why we are considering this 11 to 19 tray as a single envelope. Okay, there is no change of notation. I mean, the notations are uniformly defined for 11 to 19 trays. In fact, the same is true for second to 9 trays. Only feed tray has a little different notation because capital A and capital Z, they are involved with the feed tray. So we will model the feed tray separately. From second to 9th tray, 11 to 19th tray, there is no difference in notation. I mean, notation are, quite uniformly defined. But in the feed tray, which is in between these two envelopes, that includes two new terms. One is capital A and capital Z, feed flow rate and feed composition. That's why we will develop separately the model equation for the feed tray. So let us consider this as nth tray. Okay, this is nth tray. Nomenclature, what is written here is quite obvious. And I think there is no difficulty to understand the total and component mole balance. You see, it is quite straightforward to write the total mole balance and component mole balance equation for a typical nth tray, which is a generalized tray. So if you have finished this one, you go for the feed tray. If you have finished the modeling equations for a typical nth tray, you go to develop the model equation for the feed tray. Next, you go to develop the two modeling equations for the feed tray. You see, are you getting this equation for feed tray? Anyone got this? Got this equation, anyone?
Yes, sir.
Okay. Component balance. See, remember this thing, you do not multiply with composition for component balance with these terms. Do not do this mistake. Okay. You multiply the composition with the original terms here. Do not consider this one, this simplified term. Okay. Because although the flow rates are identical, all vapor flow rates are identical, but their compositions are not identical. Vapor flow rates are identical, but their compositions are different. So you do not multiply with this. Okay, let us take 5 minutes left, then we'll come back again. Yes. So let us come back to the model. So all of you did this modeling of feed tray. Okay, what is the next then? Bottom tray. You see the bottom tray. This is in fact fast tray. So accordingly, the notations for liquid and vapor flow rates and their corresponding compositions are used. This is the total mole balance equation dm1 dt. dm1 dt, this is the total mole balance equation. Roll number 10051, Subham Kumar. Subham, are you there? 10051.
Yes, sir.
Tell me, what is the component mole balance equation for the first tray? Just tell me the terms here. Did you write it or no?
Sir, not.
You are not?
I didn't write it.
You write it and let me know.
Okay, sir.
Carry on. Shukda Murmu 10056.
Yes, sir.
Tell. Component mole balance equation for this bottom tray. Tell me the terms.
Sir, YBVB.
You start from the left hand side. This is the reference equation, total mole balance. Just you write
L.
now. Yes.
Sir, L2x2 minus L1x1 plus
Then
V2YB.
term is not there.
VBYB minus B1Y1.
What is in the left hand side? Tell me the left hand side.
L2x2.
Left hand side, that is right hand side you were saying, no? Differential term, accumulation term. Okay, 10051 Subham Kumar. Can you tell the accumulation term? 10051 Subham Kumar, I asked you before. What is the left hand side term? You do not want to give the answer. Okay, no problem.
Sir, I'm just writing it.
You see, this is the equation. Now the last and bottommost term is column base reboiler system. The bottommost section or envelope is the column base reboiler system. This is the bottommost envelope, column-based reboiler system, and modeling equations are quite straightforward. Is this clear, students? Or you have any doubt? The modeling is quite straightforward for this distillation column, especially what we have discussed so far. Okay, so you see all the equations are ordinary differential equations. All the modeling equations for so many envelopes we have discussed so far are ordinary differential equation, and in fact this is an initial value problem. All the modeling equations are ordinary differential equations, and this is an initial value problem, IVP problem. Okay, now but these apart from these modeling equations, there are many algebraic equations involved which are supporting equations. I repeat, along with these ordinary differential modeling equations, there are several algebraic equations involved in this model, which are basically supporting equations. Those equations we want to also discuss along with this. I told before I will discuss this term relative volatility, which is represented by alpha. You see, this is alpha expression. Alpha ij means relative volatility of component I with respect to component j. So here you may consider I as component A and j as component B. Accordingly, alpha AB is the relative volatility of component A with respect to component B. Now what is K? K is vapor liquid equilibrium coefficient. K is vapor liquid equilibrium coefficient. If you recall the tray, over a tray, vapor and liquid phases are in contact. Okay, so vapor and liquid, there are two phases existed over a tray, and they are at equilibrium condition. They are at vapor liquid equilibrium condition. If they are exactly at equilibrium condition, then tray efficiency is considered 100%. I repeat, there is vapor and liquids over a tray and they are in equilibrium. They are in phase equilibrium. If they are truly in phase equilibrium, then we can consider the tray efficiency as 100%. I mean, trays are 100% efficiency. In fact, this is considered in our assumption. But in practice, these vapor and liquid phases are not in equilibrium, are not in phase equilibrium. In that case, we consider a tray efficiency which is definitely less than 100. So tray efficiency basically indicates the departure of two phases from equilibrium state. Now Ki and Kj, they are represented by these equations, which are quite simple. You see, vapor phase composition or vapor phase mole fraction Yi and liquid phase mole fraction Xi. So Yi by Xi, this is Ki. And Kj is similarly Yj by Xj. Y is vapor phase mole fraction and X is liquid phase mole fraction. For a binary system, we can write Xi plus Xj equal to 1, Yi plus Yj equal to 1. These are the summation equations. These are sometimes called summation equations. So for our example system, it is x1 plus x2 equal to 1 or xa plus xb equal to 1. Similarly, Ya plus Yb equal to 1 for the vapor phase. Now come back to the alpha ij. So accordingly, I can write alpha ij in this form. Fine, I think you understood this. Now if you rearrange this equation, we get this. If we rearrange this equation, we get the expression for Yi. Is this expression correct? Anyone can confirm me? Is this equation correct? Anyone can confirm me? Three 0019 Sasank Gautam.
Yes, sir.
Yeah. Is this correct?
Yes.
Or you did not get yet?
Right. I get. Right.
Okay. So you see what we are doing basically, we are just trying to develop the model for calculating all the variables. Okay. We are just trying to get the model equation to find all the variables. So this is the equation using which we can calculate Yi or vapor phase mole fraction. Now, alpha ij is usually given to you and it is a constant quantity for all trays. Knowing this alpha ij and xi, we can calculate Yi. This is the final expression for computing Yi. And here one typical example is given. like alpha is equal to 2 for 1 propanol ethanol system. This is a typical example. Next, come to discuss the calculation of liquid flow rate. How you can calculate the liquid flow rate? That we want to know next. So this equation is popularly called as Francis-Weir-Trey hydraulics equation. Francis-Weir-Trey hydraulics equation. This equation is popularly called as Francis-Weir formula. So this is the flow rate of a liquid stream leaving nth tray. This is the flow rate of a liquid stream leaving nth tray. This is its corresponding steady state value, ln naught. Similarly, mn naught is also the steady state value for the hold up over nth tray. I mean, steady state value of mn is mn naught. Steady state value of mn is mn naught. Mn is the instantaneous liquid hold up on nth tray. And beta is a constant which is called hydraulic time constant. You can adopt the value for beta in between 3 to 6 seconds per tray. Now let us come to discuss how we can calculate these values. In fact, I would like to ask this yi equation also. You see, this is the equation, yi equation. I mentioned before that alpha ij is given to you, like I have given here for a particular system. In fact, you can get this value from the standard book and literature. So if I want to calculate yi, we need the information of alpha ij and xi. Can anyone tell me how we can get xi? If we want to calculate yi using this equation, alpha ij is known to us, like one example is given. You can collect this information from the standard book or literature papers. Now another variable we need to know to calculate yi, that is xi. Question is, from where we can get this xi? Anyone?
Sir, can we estimate through the temperature?
Xi, no. Oh, you are recalling that estimator.
Yes, sir.
Yeah, that is possible, but ready-made equation is available. In fact, we have discussed before the derivation of this yi expression. From there, you try to give the answer. Anyone else?
Sir, from component mole balance.
Absolutely correct. What's your roll number?
19CH30036.
Yes. From component mole balance equation. I have mentioned, no, these are, this is basically the initial value problem. Now you see, if you come to suppose this equation, if you solve this equation, you will get x20. If we solve this component mole balance equation as an initial value problem, we will get x20. Correct answer. Yeah, now next come to this equation. Can anyone tell how we can calculate Mn? Let us discuss one by one regarding all the right hand terms, how we can get them. How we can get the information on Mn, liquid hold up on nth tray.
So this will be total mass balance.
Yes. Mn we can get from the total mole balance equation. You see here. If you solve this ordinary differential equation, we can get Mb. So you recall, from the total mole balance equation, we can calculate the liquid hold of M. From the component mole balance equation, we can get the liquid phase composition or mole fraction X. Fine. Third one is Y, that we can get from this equation because all the right hand terms are known to us. Fourth one is this liquid flow rate calculation. Mn is known to us. What about Mn naught? Steady state value of Mn. Anyone? See it's yeah. Anyone?
Sir, we can make the rate term 0, so then we can find the steady state value.
Okay, after simulation you were saying keeping left hand side 0. Okay. See, if you consider this is an initial value problem, that means you need to consider or adopt some initial values for Mn and Xn, no?
So
If this is an initial value problem, you need to adopt the initial values for M and X. Fine. So usually what we do, we can arbitrarily choose this Mn value at time t equal to 0. But is there any way to assume even this Mn value more correctly? Answer is in tray geometry. You know the tray geometry, no? It's a cylindrical tray. Okay, if you know the tray diameter, if you know the tray height, that is outlet wear height, it's a cylinder, pi r square h. You can easily calculate the volume. Now, if you see the tray, 80% suppose it is defined in the tray geometry, you know. 20% of the tray volume goes to the downcomer. Rest 80% remains for the liquid holdup. So you can easily calculate the volumetric holdup. After knowing volumetric holdup, you just multiply with rho. Then you will get Mn naught. I repeat, your tray is basically a cylindrical tray. Diameter of the tray must be known to you if you design the column. Height of the tray, that is nothing but the wear height. Wear height is in standard dimension, you know, usually it is 1 inch. 1 inch or maximum 2 inch, which is for a very few cases. It is true for the industrial columns. So height is also known. So we can calculate the volume of the tray, pi r square h. Now 20% of this volume is going to the downcomer section. That means 80% of the volume is basically dedicated to holding the liquid. So volume is known, this is volumetric hold up, we can tell. Now if you know the rho of the rho of the liquid mixture, then we can easily calculate Mn naught. Fine. So this is basically the initial value we can adopt to solve this initial value problem. It is better than arbitrarily assuming Mn at time t equal to 0. Yeah. Any answer for Ln naught? Anyone? What is the initial value we can adopt for Ln naught?
So you said the 20% that falls from the tray, that can be considered the L and not.
20% I told.
So basically what falls from the tray.
Yeah, but this is flow rate, no? If you think about total amount, it's okay, but this is flow rate. That means mole per unit time. It's difficult to calculate from there. Better calculation you have in your hand. Think. Okay. So I think this question is left for you. I am giving the answer of all questions. You think about this, how you can calculate L and not. Fine. And beta I have mentioned, you consider in between 3 to 6. Any value you can pick up, maybe 3, 4, something like that. Fine. Now come to the vapor boil-off. Vapor boil-off calculation. I mean, we are considering all vapor flow rates are identical. But thing is that any one vapor flow rate you have to know. Otherwise, you do not have information of vapor flow rates. I repeat, we have considered all the vapor flow rates are identical. So identical to what? Certain value, no? That certain value is suppose VB. And VB we have to know, then only we can have the information of all vapor flow rates. Now that VB we can calculate based on this equation. Question is how we can know the right hand sides? How we can know QR? How we can know lambda B? Anyone? Do you have answer? How we can know QR? That is reboiler duty. How we can know lambda B? That is latent heat of boiler vapors or latent heat of reboiler liquid.
Sir, reboiler is nothing but heat exchanger, so we can use equation of heat exchanger MCP delta T to calculate QR reboiler duty.
MCP delta T. No, this is not the correct term.
Not MCP delta T, but M dot Cp of hot fluid into temperature change of hot fluid, because we are heating up the cold fluid, which is we are heating the liquid in the reflux drum, right? So no, sorry, we are condensing it. So
yes. Now come back to the earlier question. I mentioned no. This is superheated steam or saturated steam. Yeah, you are in fact in correct direction. You were saying condensing.
Yeah. So
Correct. Now correct the equation MCP delta T. You just correct that equation. Replace that equation.
okay.
See, let me put the hint like this way. There are two types of heat. One is sensible heat, another one is latent heat. Sensible heat we calculate by MCP delta T. Agree? What about latent heat? How we can calculate that? M into lambda. M into lambda, that is the way we calculate the latent heat. Okay.
Yes, sir.
Yeah. So it's not MCP delta T. MCP delta T is used to calculate the latent sensible heat. So here just we use steam in the reboiler, and this steam basically releases heat by condensing. Through condensation, the steam releases latent heat. So that heat which we are representing by QR is equal to basically M steam into lambda steam. I repeat, QR equal to M steam multiplied by lambda steam. Agree? So you are understanding that we have the information on QR, because steam flow rate you can easily calculate by employing any flow meter, and lambda S is also we can calculate. Yes, now come to the lambda B. In fact, we will get the answer how we can calculate lambda S also. How to calculate QR in the right hand term we discussed. Now the variable which is left here, that is lambda B. Anyone can give the answer how we can calculate lambda B, or any other way to have this information? Yes. Anyone? Okay, you first give the answer. How you can know the information on lambda S, latent heat of steam, which is required for the calculation of QR. Yes.
Sir, from steam table.
Correct. Roll number.
Sir, 19CH30036.
Yes. So steam latent heat we can get from steam table. Now question is how you can calculate lambda B.
Sir, I guess from some Paris handbook or some standard.
No, you have to tell how. I'm not asking the book. You tell how you can calculate it. Oh, you are saying that you are directly trying to get the lambda value, constant value?
Yes, sir.
Oh, yeah. In that case, it's true. You can get the lambda value for any component from any standard textbook, data book, sorry, not textbook, data book. Now, see, steam is pure steam, but here lambda B is basically lambda for a mixture of component A and B. Here B is not the component, it is for the bottom. Okay. I repeat, this latent heat lambda B basically includes the latent heat of two components, A and B. Question is how you can calculate. Now give the answer.
Sir, we can take the composition and from the mole fractions of that from the mole fraction of each component, we can weight the latent heat of each component and then add it up.
Yes, this is also correct answer. So sum of xi lambda I. Agree? Lambda B equal to
yes, sir.
Summation of lambda I into xi. We can calculate by this way this lambda B. Now my question is, if I want to consider this lambda as a variable, not constant, is there any way? I repeat my question. Lambda for a particular component you are considering constant, and therefore you are taking the value from any standard data book. My question is now lambda is not constant. We want to vary it to get better results. How we can calculate lambda? Yes.
Rather than using summation, we can integrate it like by expressing it as a function.
Yeah, what function is that? Any standard equation is there? You have started, you are in correct direction. Move forward. Is there any equation?
For latent heat of vaporization.
Any equation? I hope you have started in your process calculation course. Anyone? Anyway, what's your roll number? Who told a function?
19CH10019.
Yes, this is also in the right direction. Anyone can tell? I mean, what equation or which form of lambda we can integrate? Three 0024 roll number. Yeah, Boru.
Yes, sir.
Yeah. Any answer do you have?
Sir, I'm not sure whether you want a specific equation or I'm assuming it's an empirical form of the latent heat. I mean, which depends on temperature and a few
Sir,
constants.
integral form of Clausius-Clapeyron.
Correct. What's your roll number?
19CH30029.
Yes, absolutely correct. Clausius-Clapeyron equation. I think everyone can recall this equation. Clausius-Clapeyron equation. In fact, 24, Bandhu, what you told, that is also somewhat correct. That is function of temperature. So if you see the final equation of Clapeyron equation, lambda is basically function of temperature and two Antoine constants B and C. Okay, one student or someone told that empirical equation. Yeah. So answer is Clapeyron equation, using which we can calculate this lambda B for a mixture. If we do not want to consider the constant value of lambda for component A and component B. Okay, we want to end here today. If you have any question, you can ask me. Otherwise, we will end here. Anyone have any question? No. Okay, then. Thank you to everyone.
Thank you, sir.
Thank you to everyone.
Thank you, sir.